All right. Hello, everybody. Um, Thank you for joining us for this presentation, for joining us in this webinar. I think I've given enough time for everybody to log in. If not, they'll be let in by, in the background, my friend Michelle. Cool. So thank you again for joining us for this webinar. My name is Ramon Burgos. I am the HB Sales Manager. I hope everybody can hear me and everybody can see the screen, the presentation on your screen. Although your cameras and your microphones have been disabled, feel free to reach out to interact with me through the chat box on your Teams app. You could either do it through the chat box or in the Q&A tab. So this webinar will be focusing on Haefely's FRA 5311. So this is Haefely's solution to sweep frequency response analysis. So if you've joined us previously for our previous webinars on the HV side, in June, we went through the WA 2293, which is the winding resistance and TTR combo unit, and it has many other functions. And in August, we spoke about, I gave a presentation on the Midas Micro 2883. So with this presentation, the FRA 5311 basically kind of rounds out like what we like to call our sort of low voltage substation testing equipment. So you have your winding resistance, turns ratio, short circuit impedance for transformers with the 2293, tan delta and capacitance with the Midas Micro, and then finally we'll do the sweep frequency response analysis with the FRA 5311. So basically, I'm going to get into really quick just the instrument itself. We'll get through some information on what frequency response analysis is, and then we'll give you just show you some of how the software works and how you can use the software tool that comes with the instrument to analyze your curves and do a whole bunch of cool stuff. So getting right into the product itself. So the FRA 5311 Sweep Frequency Response Analyzer is Haefely's solution to detect transformer winding movements, mechanical failures due to mechanical shock, transmutation, or short circuits. Currently, it is the smallest and lightest instrument in the industry. As you can tell, it's 5 inches across and 6 inches and a bit more, 6.69 inches. So it's basically a small box, weighs only a pound. So basically you could set this up just about anywhere. And so one of the great things that I like about the 5311 is it's just so easy to connect and set up. Basically, all you need to set up is a laptop computer and your FRA. So you will connect it via USB to your computer. And then we have 2 sets of cables. One is a twin BNC cable that will have your generator and your source connected to it. And then you'll have a single BNC cable that will connect to your receiver. So in the front of the FRA, you have your channels for your source and your generator and your receiver, channels 1, 2, and AWG, which is your generator. And basically that's it. Once you connect to the computer, and once you connect your 2 clamps, you're basically good to go. The FRA, I should mention, is completely fulfills the current industry standards according to IEEE C57.149 and the IEEE C57.149 standard. So just to highlight just a few of the features, the FRA 5311 has great, really high signal to noise ratio. Uses an 11-volt peak-to-peak voltage at 50 ohm impedance. So basically what this high signal to noise ratio will allow you to be confident that the measurements that that you're receiving or that you're picking up are definitely from your transformer and not from any noise sources that could be influencing. It will measure the magnitude, your phase, your impedance, I'm sorry, admittance and ratio. It will, the software comes with predefined test sequences for the most common transformer configurations. So it's easy to set up and kind of helps guides you through so that you avoid making any wrong measurements. The analysis tool on the software, you can easily find faults, compare curves, you can analyze the results. You can go on the field, do your measurements, and then take the curves that that were produced, and you can take them to your office. You don't necessarily have to be connected to the device to do analysis of the curves. And one final feature that I think is pretty cool is that it also is compatible. It complies with the IEC 676-18 Appendix E XML file format. So basically, all the major manufacturers uh, will have this XML file format, and what that'll allow you to do is that you can take measurements done with the FRA 5311, and you can import measurements done with other manufacturers' instruments. So so that way, if you get to a site and all they have is info from another instrument, that's no problem. You can just load them up into the software analysis tool, and you can go ahead and compare using the curves that you obtain from the FRA 5311. So basically, when you order your 5311, you will get the following. You will get your 5311 measuring device. It comes in a hard shell case with with a external power supply, which is not necessarily you don't necessarily need to use it because it does power on through the USB. You'll also get a USB drive with the software and and a PDF version of the manual. And then you'll also get a cable bag, and in that cable bag, you'll get your 2 measuring clamps, as I mentioned before, 1 measuring clamp for your twin BNC cable, which is a 20-meter cable for your generator and source, and another 20-meter cable for your single BNC cable with the integrated 50-ohm termination for your receiver. You'll also be supplied with 2 ground tapes, each 10 meters with the connecting clamps, which are basically like a vice grip plier that you see in a couple slides. You also get obviously a test certificate that it's been properly calibrated from factory, and as I mentioned, the USB memory stick with your device software, analysis software, and your PDF version of the manual. So so you know about now you know about the instrument, what you'll get, but what exactly is sweep frequency response analysis? So when we're talking about uh, FRA analysis or sweep frequency analysis, we're talking about basically it's a diagnostic technique that is used for detecting changes in the electrical characteristics of a power transformer winding. So it's a non-destructive and non-intrusive test, and it can be used either as a standalone tool to detect winding damage or as a diagnostic tool to pinpoint damages detected maybe from other tests. The FRA basically consists of measuring the admittance or impedance of the capacitive and inductive elements that comprise the transformer winding. So basically, a transformer is a complex network that consists of resistive, inductive, and capacitive elements. And so when you input a voltage signal, but basically with the sweep frequency analysis, what we're doing is we're inputting a voltage signal on one side, and then we're reading the response or the transfer function of the transformer on the other side, and then that way we come up with a curve. Why is it sweep? Because this is done it is done in a range of frequencies. So we sweep from a lower frequency to higher frequencies and we plot out this curve, which is basically what in the industry we call a signature or a fingerprint. So the measurement is performed over a wide range of frequencies, and then the frequency response are compared with a reference. And then that way you can make a diagnosis of your transformer winding condition. So the circuit changes in the winding geometry generated by mechanical forces will be reflected, and even small winding movements or distortions will cause legible changes in the measured transfer function, which the FRA can clearly detect. So like I said, usually we would talk about a transfer voltage function where we're reading the output of voltage compared to the input, and then you'll get like this characteristic curve. Obviously, this curve will vary. The shape of the curve will vary depending on the winding configuration, but it is a unique fingerprint or signature for that transformer. So usually, when we use FRA, we're usually using it after some event or condition that can possibly that has the possibility of causing mechanical or electrical damage to a transformer. And some examples are, for example, factory short circuit testing. If a factory has completed the construction of a transformer, they go ahead and do a short circuit test. You may want to it's probably a good idea to run your sweep frequency analysis to uh, to assess if there was any damage during that test. It could also be used if a transformer is taken offline to be relocated, or if a new transformer has gone through some sort of transport to get to a site. So if any, it's always a good idea to run a sweep frequency response analysis on a transformer when it's after it's been transported, just to make sure that during that process, it has not suffered any mechanical damages. Also, you may use it after a significant through-fault event, say a substation transformer experiences a short circuit condition or some sort of overloading. After the event, it is a good practice to run a sweep frequency response analysis just to make sure that everything is okay. Or maybe the transformer is equipped with different monitoring devices, temperature sensors, or relay, any sort of relay that can produce an alarm. That can, maybe it's a good idea if you have an alarm condition on your transformer to run a frequency response analysis to just to make sure that everything is okay. You could also, and this kind of ties in with what I mentioned earlier. If you've done a winding resistance test or tested capacitance of your windings, and you see that in those tests you have significant changes in the values, well, maybe a good further step in the analysis of that transformer would be to run a sweep frequency response analysis, and that could help you pinpoint exactly more or less where you can be experiencing where your fault could be located within the winding. And finally, just as a regular routine diagnostics measurement protocols, as a regular maintenance tool, is always good. And maybe you have a transformer that is scheduled for maintenance every 6 months. Well, since you're already disconnecting the transformer, you're already running other tests. You might as well run a frequency response analysis as well, and have that as part of your documentation for that specific transformer. And so, tying into that maintenance sort of focus, when we do frequency response analysis test, it's important to to determine or to have a what we call a baseline measurement and know what is a diagnostic measurement. So anytime you run a sweep frequency response analysis, like since we're talking about a very unique fingerprint or signature for that transformer, a baseline measurement should be or may be conducted either at the factory or once it's in the field, and it provides information that can be used for future comparisons. So it's very important to consider, certain considerations must be taken to accurately document the testing methods and connections. Make sure you properly archive the data, verify results, and ensure the repeatability of the methods and results. So every time you go and do this type of test, the goal is to get it to be to have your test setup match as close as possible to this baseline measurement. That way you have a record or a way to compare directly. Once you're conducting a diagnostic measurement after your baseline, it's important that you match the same setup and the same parameters that you use in your baseline measurement, just so you have an accurate comparison. So so that's just always good to realize that with most diagnostic measurements, they are usually trending or based on historical data. So it's good that we keep in mind that we want to ensure the repeatability of the test results. So when we're ready to go ahead and make to do a full test on a transformer, the FRA, as I mentioned before, is very simple to connect. Basically, you have 4 steps in connecting your FRA to your transformer. Then, like most tests, these, like I think I mentioned that this is an offline test, so you will have to disconnect everything from your transformer bushings, make sure that everything's disconnected, kind of isolate your transformer, and then go ahead and start connecting your FRA. So um, basically, you have these 4 steps. You will first connect your source generator clamp, which is your first step here. And as you can appreciate here in this first image, the clamp for the source and generator is unique. It has 2 BNC cables that come out from it, and this will go on one of your bushings, whichever one, depending on the sequence. Then you'll go ahead and connect the receiver clamp, which is similar to the first clamp, only it has only one BNC cable coming out of it. It's fairly simple, so you avoid making these wrong connections. And also, each cable is color coded according at each cable end and at the instrument. So basically, just match the colors and kind of make sure that you don't have any connection errors. The clamp design, as you can see down here, the clamp design will accommodate bushings with cylindrical terminals or flat terminals. And then the third step would be connecting your ground strap. The ground strap will run from the top of the bushing all the way down to a bolt at the bottom of the bushing of your transformer. The strap in the next slide, we'll see how to properly connect the ground strap. And then finally, you just connect your USB cable to your computer and you're ready to go. Now, getting back to the ground strap, it's very important that the ground strap connection is done properly. In order to reduce the ground inductance, an aluminum copper braid is delivered with the FRA 5311. So the braid must be connected between the measuring clamp and the ground using the minimum length to avoid high frequency readings. So basically you want to connect it at the clamp. The clamp has this wing nut, so you can take out, you don't need any tools to connect the ground strap. Once you place the ground strap on your clamp, you want to run it down the length of the bushing as close as possible to the bushing. We don't want to have excess ground strap kind of floating around. We want to keep it as close to the transformer bushing as possible, down to the base of the bushing, and then using this vice grip type clamp, you connect your other end of the ground strap and make sure you bolted on a nice clean connection on your bushing base. Once you again, 4 simple steps for connection, and then you can go ahead and start your measurements. Now, so what exactly will we be measuring? So the IEEE C57.149 standard, and this is just a recommendation for a two-winding three-phase transformer. So there's basically two basic measurement or test types, and then there's two others that could be helpful as well. But basically, we're talking about a high voltage open circuit test, where everything is left floating. And then we have that'll be done high voltage and low voltage. And then we'll have a short circuit test where you'll short circuit the secondary bushings and then run your test according to the sequence. So IEEE has, for example, 9 steps in this sequence where you'll test different configurations, H1 to H3 and so forth, depending on your winding configuration, or if it's a single phase transformer. The good thing is that the FRA 5311 has all of these standard IEEE standard sequences pre-programmed. So basically, all you have to do is bring up a template and then follow the instructions on the template. It'll guide you through each one of the sequences. And then after you're done, these 9 curves that will be produced from each test, you can put them in the analysis tool all together and do your diagnostic analysis. So once you run a test, you do your sequences, you'll start seeing results very similar to this curve that's on the screen right now. And so again, depending on the frequency, there will be different responses. Different parts of the transformer will start responding to the voltage signal that's being injected. So although it's not a certain science, but it's widely accepted that anywhere between 20 hertz and 2000 or 2 kilohertz, the response that you're getting is going to help you determine if there have been core deformations, open circuits, shorted turns, or residual magnetism. Then from anywhere between 2 kilohertz to about 20 kilohertz, that'll give you a sense if there was a sense of any faults due to winding movements relative to each other, or of the clamping structure of the core. In the next region, between 20 and 400 kilohertz, more or less, it'll give you some insight as to a fault due to deformations within the main and the tap windings. And then once you get from 400 kilohertz up to 2 megahertz, which is the top of that the standard requires, the standard requires that it has, the requirement is up to 2 megahertz. That will go ahead and give you information about any movement in your main and tap winding leads. So basically, you'll have this characteristic curve, and you'll be able to with the analysis tool, be able to superimpose them one on top of each other, or have your historicals, put them on one on top of each other, and that's where you'll be able to kind of gauge the differences between each curve. So, and all of that is done with the software tool that is included with the 5311. So the FRA software has two main operating modes. The first mode is the measurement mode. So in this mode, it's similar to what's on your screen. You have a space where you can define your parameters, where you want to start your frequency sweep, where you want to stop it, what type of on your x-axis, what type of uh, uh, sweep what type of sweep you want, whether you want it to be logarithmic sweep, or give you a logarithmic plot, or you can do a linear plot. You can choose how many points you want to sweep, and you can also choose at what voltage level you want the signal to be at. So the maximum for the 5311 is 11 volts peak to peak, but you could do it as low as 100 millivolts if you wanted to. So then also you can go ahead and put in some information about your connections, and in these fields, this is what's going to be showing up on your curves, giving the names to your curves. And then the measurement, and then once you basically have all this information, you can go ahead and set up your a single or a manual measurement, or you can go ahead and to the sequence tab, and you can go ahead and choose one of the pre-programmed templates to do a full sequence on your transformer. So this is what it looks like for the pre-programmed sequences. Like I mentioned, it has a pretty diverse list of sequences according to most common transformers configurations. So basically, you choose your template, whether it's a three-phase, two-winding, delta-delta, or if you have a three-phase, three-winding with delta Y delta. You choose with your transformer configuration. It'll give you as you can see, the 9 sequences that are required by the standard. You hit OK, and then you can go ahead and start your measurements. Once you have your measurements done, you can switch to the analysis mode. And then in analysis mode is where the collected single measurements can be loaded together, compared, and analyzed. So this analysis tool also, will give you all those, will display the curves, and then it also has these different functions where you can choose with the cursor, you can choose to find the difference between two curves, or what they call the coherence between two. You could also choose to process one curve what they call processing, which will kind of refine the curve and make it a little bit more precise. Or you can do a comparison with, for example, the Chinese standard. It'll compare to the Chinese standard directly. And all of that you can go ahead and print it. It'll come out on your XML report, which could be opened up in any browser. And since it follows that IEEC 600 Appendix E file format, you can take it between different measuring tools, measuring instruments. You can compare curves from basically any manufacturer that uses that same XML file format. So like I mentioned, you can compare up to 10 measurements on one screen. The cursors can easily be placed and gives information on each measuring point throughout the whole sweep. You can calculate differences of curves, and or coherence between two or more curves. It all could be calculated using this software, the analysis mode on the software tool. Again, easy to use interface. It allows you to load the measurements, set configuration, obtain connecting information, and program your sequences. And as I mentioned, test reports can be exported as a CSV file, but as well as the standard XML file format. And so that's where you'll have the ability to go between the IEC XML. You can come in with a Megger or a double curve and load them up, and you won't have any problem using that mix of curves with this software analysis tool. So in the next slide, next two slides, I'm going to go ahead and play some videos that will basically just go again through basically what I've been talking about up to this point. So the first one is just an overview of the instrument, and then on the second one, you'll kind of get a sense of like a quick start video on how to use the instrument. So go ahead and pull up the first video. So that was first just the overview, and this is all obviously what I spoke about earlier, that you can combine this with our other instruments for a complete transformer analysis setup. I'm going to go ahead and play the second video, which will go through, it's basically like a setup, a quick start guide. Enjoy. All right. So basically that I guess that pretty much sums up uh, the presentation for the instrument.